So the next concept is Moculloh-Pitts neuron model. We have already seen in the last class operation of biological neural network and different types of biological neural networks, characteristics of artificial neural networks, and also how we connect the neuron, biological neural network with the artificial neuron model. And so we design the basic artificial neuron model. Coming to the types of artificial neural models, basically there are three types of artificial neural models based upon the type of activation function used, and based upon there are different types, but the most important simple models are three types, and they differ based upon the type of activation function and also based upon the training that they undergo and based upon the inputs and weights that are fed to the neural network. So the basic types of artificial neural network are, first one is Moculloh and Pitts neuron model. So the first one is Moculloh Pitts neuron model. Second one is perceptron neuron model, and third one is Adeline neuron model. So what is meant by Moculloh-Pitts neuron model? It is a simple structure of artificial neural network which was designed by two scientists named as Moculloh and Pitts. So this is the neuron model which was designed by two scientists named as Moculloh and Pitts. And next, what is perceptron neuron model? It is the advanced version of Moculloh-Pitts neuron model, and the Moculloh-Pitts neuron model doesn't have the training. Nothing but updation of weights is not accepted in the Moculloh-Pitts model, or updation of weights, changing of weights or adjusting of weights is absent in Moculloh-Pitts neuron model. And that is the disadvantage of Moculloh-Pitts neuron model, and that disadvantage has been converted into advantage in case of perceptron neuron model. Where in the perceptron neuron model, it is equivalent to Moculloh-Pitts neuron model, but the difference between two neuron models are, in the perceptron neuron model there is weight adjustment. So whenever the weights between the layers are adjusted according to the requirement, then obviously we can say that neuron undergoes training. So whenever a particular neuron undergoes training, then obviously we can say it has become an expert system, and if we provide some data to that expert system, then that gives the correct output. So that trained network can provide accurate output. So that is the difference between Moculloh-Pitts neuron model and also perceptron neuron model, with the difference of adjustments of the weights is possible in perceptron neuron model, or we can say learning algorithms have been adopted in perceptron neuron model. And third one is, and here the perceptron neuron model is also designed by a scientist named as Perceptron Rosenblatt. And third model is Adeline neural network. The difference between Adeline and perceptron and Moculloh is, it is also equivalent to Moculloh and perceptron, but here the basic difference is Adeline is nothing but adaptive linear neuron model. Nothing but linear activation function will be used in this neuron model, and it is same as Moculloh-Pitts. The difference is it uses linear activation function, and also it is equivalent to perceptron in the parameter of training. So this Adeline neural network structure is same as Moculloh-Pitts and training is same as perceptron neuron model, with the difference of linear activation function will be used in Adeline neural network. So these are the three basic types of artificial neural networks. First one is Moculloh-Pitts neuron model, perceptron neuron model, and then Adeline neuron model. So first one is Moculloh-Pitts neuron model. So this is the basic structure of Moculloh-Pitts neuron model. So it was designed by two scientists named as Moculloh and Pitts. So here, coming to the elements within this Moculloh-Pitts neuron model. It consists of inputs. We can write with X or we can represent with I also. So that is in general represented as X. So first input is represented as X1. Second input is represented as X2. Third input is represented as X3 and so on. Let us consider Xn or the n inputs for this neuron model. Now, whenever inputs are obtained for the neuron, what will happen? All the dendrites and synapses are going to collect that information. So here, this information is being collected by weights, or we can call them as synaptic weights. So for collecting the information of X1, synaptic weight of W1 will be used, and so it is represented with W1, which represents synaptic weight of first input carrying an input information of X1. In the same way, second input consists of weight of W2, third input consists of weight of W3, and so on. N input consists of weight of Wn. So this is how we are having n number of inputs in the input layer, and we are having n number of weights which carries n number of inputs. Now, as the weights carry this information, then what is the total input at this first input layer or first input neuron? So we need to multiply this X1 with W1 because this weight carries this information of X1, and so our output at this input layer is X1 W1. In the same way, at the second input we will get an input of X2 W2 and then X3 W3 and so on Xn Wn. These are the n number of inputs that we attain at this input, and as we are getting input with the weight, and this layer we can call it as input layer, where we are collecting inputs with the help of synaptic weights, and we can call that layer as input layer. Now after multiplying weights with the synaptic weights with the inputs, at each input we are getting weighted input. We can call this as weighted input because we are going to multiply that weight with the input, and so this is called as weighted input. Now we will get a weighted input at the input of this particular neuron. Now we are getting n number of inputs. We are going to send all these n number of inputs to summer block. This is called as summation or summer block, and this summer will sum up the entire information of this n weighted inputs. So the output of this summation block we can call it as X net. We can write it as net input value at the output of summation block. X net is equal to, now at the summer all the inputs are coming. The first input is X1 W1. Now this summer will add plus X2 W2 plus X3 W3 and so on. We are going to add n number of weighted inputs. So we will get Xn Wn. So X1 W1 plus X2 W2 plus X3 W3 and so on Xn Wn. in addition to that, already I have told you, in addition to these weighted inputs, we will also consider other input which is called as a bias, or its weight is represented with 1 B, and its input is always equal to 1. So what is the input we are getting with the help of the bias? B into 1, because bias is having, let the weight be B, and always the input of this bias will be 1. So based upon the value of this bias weight, we will get some value here. So here this B into 1 we will get as B at this. Now in addition to this weighted input, we are going to add the bias weight or bias input value. We can write it as B into 1. So we will get B. So this is the net input that we can collect at the summation block. So first one is X1 W1 is the weighted input, where weight is X1 and input is X1, weight is W1, and weighted input at the first input will be X1 W1, and second input is X2 W2, third input is X3 W3, and so on. Nth input is Xn Wn plus B plus a bias value. In general, bias is used based upon the summed weighted input. So this is used to limit the weighted input value. So this is how we are getting X net. And this will be obtained at the output of summation block. So this is how we will get X net. Now this X net is passed through threshold function, or we can call it as activation function. The weighted input is passed through threshold function or activation function. And in general, there are different types of activation functions, of which Moculloh-Pitts neuron model uses binary step activation function or step activation function. So this uses step activation function. So what is the step activation function waveform? So the step activation function consists of a time period with a value of theta, and a time period of t. So this is step activation function. We have already attained a net value of X net at this output of summation block. Now if this is sent to step activation function, what will happen? This step activation function is having an activation value of theta. Nothing but if X greater than or equal to this theta, then output of this activation function will be 1. If X less than theta, output of activation function is 0. This is the general expression for binary step activation function. So here, what is this X? X is the input that is passed through this activation function, and it will compare this X with the value, activation value present in the activation function. And here, if the provided input for this activation function is greater than or equal to theta, then we will get output of this activation function as 1. And so this is called as step activation function. And here, if the condition is not satisfied, nothing but if X is less than theta, we will get output as 0. So this is about step activation function. Now what is X in this Moculloh-Pitts neuron model? What is the input we are sending it for? The activation function. The input that is being sent to this activation function is X net. So X net is fed to activation function. So X net is fed to activation function. Now this X net is going to be compared with threshold value, that is based upon your load requirement where you are using the Moculloh-Pitts neuron model. The activation value will be decided. So here if you see, if X net, it is passed through the activation function, binary activation, step activation function, and so if X net is greater than or equal to activation value, then the output of this will be 1. Output of the neural network is 1. Now, if X net is less than theta, it is not satisfying the condition, then you will get output of this neuron as 0. So this X net is being compared with the activation value present in the activation function. If the condition is satisfied, we will get 1 as the output of the neuron model. If the condition is not satisfied, we will get 0 as the output of the neuron model. And here, if 1 is obtained as the output of the neuron model, now we can say that a neuron is fired. We can say that neuron is fired. Neuron is fired and information through that neuron is passed. And if we are getting output of this neuron as 0, we can say that neuron is not fired and we will get output of this, or information is not passed through that particular neuron. So once we will get the output of this neuron, let it be Y, then this output will be fed to other neuron as an input. And here if we see, as we are getting n number of inputs with the weights, this entire layer, it is called as input layer, and as we are getting output at this output layer, this is called as, not the output may not be 1, it can also be n number, but here we are considering only one output in case of Moculloh-Pitts neuron model. And this layer where we are getting an output value is called as, so this is called as output layer. Output layer. So the layer of inputs where we are getting through the n number of weights, that is called as input layer, and the layer where we are computing the output, it is called as output layer. So in the considered Moculloh-Pitts neuron model, we are having n number of inputs and output will be only 1. So inputs are n, output will be only 1. So this is about Moculloh-Pitts neuron model. And here, coming to the limitations or disadvantages of this Moculloh-Pitts neuron model, it consists of only one disadvantage. Advantage is it is simple in structure, easily modeled and cost effective. Coming to the disadvantages, here if you see, while performing some action, we are getting some output of Y. And that output can be effective or accurate or inaccurate. The output Y can be accurate or inaccurate. So here, if we want output as 1, but we are getting output as 0, how will we get outputs? Initially, we will get the inputs from other neurons and we will assume these weights. The weights are in general assumed from 0 to 1. So based upon this assumption, we may get output as required value or we may not get the required value. So sometimes we may not get the required value. Now what will we do? We can't do anything. The process will stop there itself. So as the initialization of weights is purely random, we may not expect a required output at the output of the neuron. If the expected output is not obtained, then there will not be any learning also. There will not be any adjustment of weights that is proposed in this Moculloh-Pitts neuron model. So the output may be inaccurate sometimes So that is the disadvantage of McLaughlin's neuron model. Here, as the weight adjustment is not there, as learning or training of the network is not there, obviously we may not get the accurate output, which is the limitation where it is avoided in most of the applications, and it is also a disadvantage of McLaughlin's neuron model. So this is about the entire structure of McLaughlin's neuron model. And now let us consider an example of execution of McLaughlin's neuron model. So basic applications of McLaughlin's neuron model is, it is in general used for realization. It is used for realization of gates. Nothing but by using this neuron model, we can execute different types of logical operations. Like we can execute AND, we can execute OR, NAND. In this way, we can implement more number of logical operations. So we can also design combinational circuits or sequential circuits with the help of this McLaughlin's neuron model, which is the application of neuron model, McLaughlin's neuron model. And here we have considered an example where we are using McLaughlin's neuron model for the execution of AND gate or AND logical operation. So what is the AND gate truth table? We'll have two inputs. For a basic AND gate, we'll have two inputs, x1, x2, and there is only one output. Let us consider it as y. And then the inputs for this neural network are in general 0, 0, 1, 0, 0, 1 and 1, 1. And output of this AND gate, so we will get output of AND gate as 1 if both the inputs are 1. If not, even if one of the input is 0 or both the inputs are 0, we will get output of this neural network as 0. So that is the AND gate truth table. So 0, 0 will get output as 0, 1, 0, 0, 0, 1, 0, 1, 1. Here both the inputs are 1. So we will get 1. This is the logical truth table for AND gate. Now we are going to implement this AND gate entire truth table for McLaughlin's neuron model. So coming to the McLaughlin's neuron model structure, it consists of two inputs x1, x2, which are passed through two weights W1, W2. And here we are going to consider activation function of step, which is having some activational value of theta, and the output is y. So the inputs are already defined. 0, 0, 1, 0, 0, 1, 1, 1. These are the inputs. Weights, I have already told you, we will initialize the weights by random nature in between 0 to 1 or 0 or 1. Or sometimes we can also consider the weights as -1 also. So, and then, so here the inputs are, these are the inputs. So we are going to perform 4 steps of operation in order to implement AND gate using McLaughlin's neuron model, where initially inputs are fed. Step 1, inputs of 0, 0 are fed, and weights of W1, W2 are initialized as 1, 1. So here in step 1, x1, x2, inputs are 0, 0, weights W1, W2 are 1, 1. So these are the weights we have randomly considered, and activation value theta is 1.5. Now what will we do? We need to first step, we need to multiply inputs with the weights x1 into W1. So x1 into W1. What is x1? 0. What is W1? 1. You will get 0. Next, x2 into W2. What is x2? Again it is 0. W2 is 1. So you will get 0. Now, after finding out x1 w1 here and x2 w here, what is the next step? We need to add this weighted inputs. So we are going to add the weighted inputs. Then we will get a net input value. How will we add? X net is equal to, we are having only two inputs, x1 w1 plus x2 w2. So what is x1 w1? 0. x2 w2 is 0. Then what is x net? Finally we will get x net as 0. Now this x net is passed through activation function where the activation value is 1.5. That is what we have considered. So now we need to consider this x net has to be compared with theta. And here, as it is step activation function, we will generate two types of outputs from this neuron. Either we can get 1 or we can get 0. Suppose here if you see, for this first input x net is 0, which has to be compared with 1.5. You know that this 0 is less than 1.5. So once this x net is not satisfied with the activation value, obviously